Let's talk about taste. Taste is one of the special senses, and personally probably my favorite taste, and that unfortunately negatively contributes to my health because I like to eat. Food tastes good and I like to eat it, and that's sort of a problem for me. But when we look at taste, we look at the tongue. And your tongue is covered with what we think of as taste buds. And these taste buds are scattered all over the tongue and actually in the back of the throat as well, but most of them are concentrated on the tongue. Those taste buds are going to be specialized. Some of them will detect sweet, some will detect sour, some will detect salty, and some will detect bitter. The textbook talks about a fifth taste, umami. And I personally very much disagree with umami being a real taste because you need to have taste buds for something to be able to detect it. And so umami is literally interpreted meaning the delicious taste. And how do you measure delicious? Delicious is not a taste, but rather is a preference of the brain for a certain combination of sweet, sour, salty, and bitter, plus texture that the brain happens to prefer. So there's no particular taste bud that says, aha, this is delicious. If that was the case and we all had them, then everyone would find the same things delicious, and everyone would find the same things lacking in deliciousness. And that's just simply not the case. What I might consider delicious and what you might consider delicious are two very, very different things. So if we truly have a delicious taste bud, well, we wouldn't have those disagreements in taste. So again, sweet, sour, salty, bitter, plus texture that your brain prefers, and that's what your brain interprets as delicious. But those taste buds are sort of scattered all over, but you would find certain areas of the tongue would have a higher concentration of sweet taste buds or a higher concentration of sour or salty or things like that. So each person is a little different. We really can't talk about taste, though, without also talking about smell, because taste and smell are really about 80% overlapped with each other. 80% of taste is smell, or if you want to look at it as 80% of smell is taste, it's the same either way. And actually, the first detectable component of taste is actually smell. So when you walk into a restaurant, if it smells good inside, you're probably going to think the food tastes good. If it smells bad inside, you're probably going to think the food tastes bad, simply because the smell was the first piece that you got. Both of those senses are literally having molecules dissolve into liquid and then be detected by receptors. So I guess you could talk about smell being tasting with your nose. And if that's the case, then we could talk about a very pleasant idea, I'm sure, and that is when you smell a skunk or some other very undesirable smell to you, you're literally tasting that with your nose, and actually some in your mouth too. So you actually, when you smell something, you're literally tasting it with your nose and to a certain degree with your mouth. So I'm sure that just makes you feel really wonderful to think about every undesirable smelling thing you've ever smelled, you actually tasted it. You're welcome. So with the smell, we can distinguish different kinds of smells, but our nose isn't incredibly distinctive in ability to separate different kinds of smells. If we were to look at something like a dog would have many, many thousands of times greater smelling ability than we would. So if food smells good, it will taste good. If it tastes good, it probably smelled good. And what we could do to sort of demonstrate that is we could put a slice of apple under the nose and a slice of potato in the mouth. They would be similar in appearance and texture. So we would say first we tasted apple, and then after we chewed on that potato in our mouth for a minute, we'd say, no, that's really potato. Or flip it around, potato into the nose, apple in the mouth, we'd first say we taste potato, and then we would adjust our opinion to say that's apple. Again, so smell, taste, really, really important that those go together. Which is why often if you have a cold or something like that and your nose gets all stuffed up, you can't smell very well, you seem to lose a lot of your sense of taste. And really you're losing that smell component of the taste. Nothing wrong with the taste buds in your mouth, but they're having to work by themselves without significant input from the nose. Vision is a little bit more complicated. And let's take this eyeball here and let's follow the path of light through this eye. So we'll start out with light out here, and it comes into the eye through the cornea, this outer layer of the eye. So the light passes through the cornea, and right underneath the cornea we have some liquid. It's aqueous humor, and it basically is just filling that corneal cavity there. That light will then pass through the pupil. The pupil is just a hole in the iris, is all it is. And the iris is the colored part of your eye. So if you have blue eyes or green eyes or brown eyes, that's the iris that you're seeing. And the pupil is just the opening in the middle of that. And that pupil is adjustable. So the iris will actually adjust itself quite rapidly based on different amounts of light availability. And if light's readily available, the iris will constrict down, reducing the size of the pupil. If light is limited, the iris will dilate, opening up the pupil and allowing more of the light that's actually there to go through and help you see. That then, after the light passes through the pupil, it comes in contact with the lens. The lens is sort of a marble-like structure right behind the pupil, whose job is to focus that light properly through the rest of the eye. And right behind the lens you're going to find vitreous humor. And vitreous humor is more of a gel compared to the aqueous humor that was more of a watery substance. So most of the eye is actually just filled with that vitreous humor. And if the lens properly focused that light, it will project it to the back side of the eye where it comes in contact with the retina. The retina is loaded with photoreceptor cells. So let's take a look at some of those real quick. We'll come back here. Here we have rods and we have cones. And so these different types of photoreceptors are what allow us to see light. And so if we have both rods and cones, we typically do, then we can see both in black and white and in color. At nighttime, our black and white receptors probably work a little bit more effectively because they're really just detecting light or no light, whereas the colored receptors are looking for color. And because color only exists in light, then when there's no light, there's no color, so they don't work so well. Meaning if you don't have enough of the black and white receptors, that really means that you're not going to see really well at nighttime. So most people typically have a healthy number of both. So there in the retina, they pick that light up and then they connect up to the optic nerve. And the optic nerve then takes that information and plugs it into the brain, where it's then analyzed and determined as to what it is. So the light went through the cornea, through the aqueous humor, the pupil, lens, vitreous humor, and picked up by the retina. Now there at the retina, right there at where the optic nerve plugs in, we will find what's considered to be a blind spot, where those receptors are plugging into the optic nerve and there aren't any receptors in that little spot, and so there's then nothing detected. But you don't, out in front of you, see an empty spot. So what happens is a process called filling in. And what happens there is the retinal cells around the edges of that blind spot actually the brain takes that information, copies it and pastes it into that blank spot, saying, I'm assuming what I'm seeing around the edges here is also what's in the middle. And when things are a little bit further away from the eyes, that's correct. But the closer something gets to the eye, the more it gets centered in that blind spot, the less of it is actually detected by those retinal receptors around the edges, and the more it starts to disappear. So right before something touches your eye, it's probably almost disappeared completely because it's centered in that blind spot, and the copying and pasting around the edges isn't catching it as well. So the question is, how does vision really work? Light passing through, and we said the lens focuses the light on the retina. And that's really the key part of vision, is the lens properly focusing the light. So when the muscles around that lens are relaxed, they pull the suspensory ligaments tight. So it's sort of a counterintuitive process. Muscle relaxes and the ligaments associated with them pull tight, but that's how it works. And that then pulls on the lens and flattens it out. So as the lens is flattened or allowed to thicken, that changes where that light is being focused. So when you're focusing on something a little bit farther away, the lens is pulled flat, or flatter perhaps. When you're focusing on something close by, the lens is allowed to relax and then become thicker as the muscles around the edge contract, and that relaxes the suspensory ligament. So basically the lens is thicker for things close up and thinner for things farther away. And that then takes that image, hopefully, and projects it perfectly onto the retina. Now occasionally that lens doesn't work like it's supposed to, or perhaps often it doesn't work like it's supposed to. So one problem with vision is called nearsightedness. And with nearsightedness you can see things up close just fine, but things further away get kind of blurry. So what's happening there is the lens is projecting that light, but it's not projecting it properly onto the retina. Rather, it's projecting it out somewhere in the middle of the eyeball for things that are far away. And the closer that object gets, the farther back it's projected into the eye because the light was already more powerful. So farther away things have weaker light energies, and it's just not as easy to project it back. One way to fix that is with corrective devices like glasses, contacts, things like that. And so a concave lens will push that image further into the eye before it hits the retina, or rather hits the lens, and then that helps the lens to more easily push the image all the way back to the retina. If you have farsightedness, that means things far away are pretty clear for you, but things up close are not, and that's because the light is being pushed too far by the lens. So instead of being projected onto the retina, it's projected accurately somewhere past the retina. So when it hits the retina, it's not focused yet. So the further away something gets, in this case, the weaker that light is and the more precisely it's focused on the retina rather than past it. So a convex lens will basically take that light and weaken it, basically in essence pushing the image further away from the eye, and then when it goes through the eye it focuses properly on the retina. In the olden days it might take the doctor several tries before they got your corrective device just right, so that it would project things accurately onto the retina. But these days with computer-aided testing, they're able to typically get the first prescription for glasses pretty much perfect, because they're able to measure how much that light is being projected and then calculate how to adjust it to get directly focused on the retina and not in front of it and not behind it. So we've really come a long ways in vision correction in the last couple of years. A third possibility of a problem here. So those were problems with the lens not doing its job like it's supposed to. This problem here, astigmatism, has nothing to do with the lens, but rather is the cornea. So the cornea was supposed to be this slightly irregular surface. Let's go back and look at that again. So here we had the cornea. It was this bulged but smoothly bulged surface. If we look at the astigmatism here, we can see that we have an irregular lumpiness to it. It's got this irregular lump up here, and that distorts the whole thing. And then instead of projecting the image straight back, it kind of starts putting it up to the side a little bit. So then you can get glasses that would have a grinding of the lens that would sort of flip the image a little bit before it hits that distortion, so that the distortion itself will correct it. And so they have to custom grind the lens to properly match up with the irregularity of the cornea, distort it one way so that the distorted cornea flips it back the other way, in this case gets it right. Now, that probably would be a little bit more difficult to correct because it's not just push it forwards or pull it back, but it's twist it a little bit while you're at it. So that's another possibility for vision problems. One approach that's more and more common with vision problems these days is LASIK, and that's a laser procedure. And they utilize the laser to adjust, basically to melt the lens and try to get it just right. There are some other options that would involve brushing the eyes and basically doing some acid treatments and that sort of thing. All of those have some problems, but I really specifically want to focus on LASIK. It's very common, very popular, in many cases produces really nice vision afterwards. The problem is, though, that many people start experiencing vision declines within 3 or 4 years after the surgery, and perhaps within 5 years after the surgery, their vision is just as bad as it was to start with. So you paid all that money and went through that process just for a couple of years of vision improvement. Some doctors are now offering lifetime warranties on their LASIK procedures, and really it's about 20 to 25 minutes per eye, so it's no big deal for them to go back in and redo it if down the road it doesn't work out like you would hope. For me personally, if I have vision problems, I'm going to go get glasses, which are going to tweak the light however it needs to for my eyes to work, and that's all there is to it. I personally wouldn't be able to touch my eyes to put contacts in and take them out. It'd be a lot of trouble for me. I'd rather just put on a pair of glasses or take them off. Thus far, my vision is decent, and so I don't need corrective devices at this point in my life. But if I do, and statistically speaking I probably will, then eyeglasses, here I come. Hearing is actually quite simple. The outer ear is there to capture sound and funnel it into the auditory canal or the ear canal. Some of you utilize the outer ear also as a decorative function to hang metal and rocks from as part of your efforts to be more cosmetically attractive or more expressive or whatever other reasoning you would utilize jewelry in your ears for. But its biological function is to capture sound and focus it into the ear canal. That sound energy then passes down the ear canal until it contacts the tympanic membrane, or the eardrum. That then causes the eardrum to start to vibrate. Directly on the back side of the eardrum is a bone called the malleus, or hammer. That starts to vibrate. Those vibrations then transfer to the incus, or anvil. And then those vibrations are transferred to the stapes, or the stirrup. And at this point you haven't heard anything yet, but you simply transferred vibrations from the air to the eardrum, to the malleus, incus, and stapes. The stapes is connected to the cochlea, this snail-like structure here, and those vibrations pass into the fluid inside the cochlea. And inside the cochlea is actually filled with a number of channels and canals filled with fluid, and in those they have these little stereocilia. And as that sound energy passes through, that then bends those little cilia in certain patterns and certain intensities. Those cilia are connected to the cochlear nerve, which then goes to the brain and is interpreted. So sound and hearing is actually detection of vibration, and that vibration pattern is analyzed by the brain and interpreted then as sound. Sound is measured in decibels, and so this table is a couple of different examples of different things you might have experienced in real life, the sound level that it would have with it, and then the effect. So city traffic noise, 80 to 85 decibels, and the effect is annoying. And if there's constant exposure, there may be some degree of irritation and inflammation perhaps of those cilia and some hearing loss. If we go up to a chainsaw or a jackhammer, or interestingly, a symphony orchestra is just as bad for your hearing as a jackhammer is, then you're looking at 100 to 200 decibels, and regular exposure more than 1 minute risks permanent loss of hearing. Then we go all the way up to over 125 decibels. That is some of these cars that you hear people driving down the road with that are really wanting to share their music with the entire town all at once. That actually would exceed the threshold of pain. So decibels over 125 actually hurt, physically hurt. And it's very likely that you're causing some real damage there. There's a discussion on hearing loss there in the book, So take a look at that, and what you'll see is that if that energy wave is too intense, instead of bending over those little cilia, it will break them off. So hearing loss is often because of damage to those cilia, especially if you've excessively exposed yourself to sound. Other possible hearing losses would be conduction deafness, and when for some reason the vibrations are not able to get through, that could be something as simple as a buildup of earwax in the ear canal, all the way up to some other thing like damage to the eardrum or any number of other things there. So a couple of different possibilities for hearing loss, but again, one of those possibilities is the damage to the cilia. So that was down there in the cochlea, but on the other side of this apparatus we find the semicircular canals, and those are involved in equilibrium and balance. So we have here, for rotational equilibrium, the semicircular canals filled with fluid, and they have a different kind of hair structure there. And as that hair structure is bent with fluid running one way or the other, that bending pattern is interpreted by the brain, and then it tells you, are you sitting still or are you rotating or spinning? And what's really interesting here is very quickly the brain gets used to this particular direction of, let's say, spin. Some of you would have grown up in the days when merry-go-rounds were allowed on playgrounds. And my generation found it fun on a merry-go-round to get it going as fast as you possibly could in a circle, and then you jump off. And a couple of problems with that. One is your brain has decided you're supposed to be spinning. And so when you hit the ground, even if you're standing upright, you immediately fall over sideways and actually start rolling across the ground usually. Not so much because the merry-go-round threw you in that direction, but because the brain thought that was the direction you needed to go to be balanced, and it made you go that way. So your brain literally made you fall down and roll because it thought that was what it needed to keep things balanced and in equilibrium at that point. The solution to that really is to, when the merry-go-round stops, sit there for a minute and let that fluid sort of settle back down, and then your brain now knows that you're supposed to be upright rather than spinning, and then you can be off and going. But if you try to take off too quickly, you'll feel at least a little bit unsteady and staggery on your feet from that. To measure gravitational equilibrium, there's some other sets of little hairs here, and they're going to be a little bit lower there, below, in between the semicircular canals and the cochlea. And again, they're measuring the flow of that fluid as well, and that tells you what's up and what's down. So gravity is always one particular direction. And that means the brain can then interpret, well, the fluid is flowing this way, that has to be down, and so if I'm pointed this way's up and this way's down. So that way the brain can not only keep track of rotational equilibrium with the semicircular canals, but it can also keep track of what gravitationally is up or down, and keep track of where the body is relative to that, so it can hopefully keep the whole system balanced. For those of you who suffer from motion sickness, car sickness, seasickness, whatever you want to call it, that happens when there's a disagreement between this inner ear system and your eyes. So the inner ear system is measuring rotational equilibrium and gravitational equilibrium and trying to keep you calibrated for that, but your eyes are also telling you what's going on as well. And if your eyes and your inner ear disagree with each other, one will say, you're moving. The other one says, you're not. Yes, you are. No, you aren't. Yes, you are. No, you aren't. And that fighting back and forth between those two systems with differing senses of input will then cause the nausea and those other symptoms of the motion sickness. The solution is either to take a medication that will dull the brain to the point where it doesn't notice the fighting going on as much, but that's not always useful. Another possibility is to get the eyes and ears in better agreement with each other. So if you're in the back seat, often people with car sickness discover that it gets better if they're in the front passenger seat. because now you can see more of what's going on around you, and your eyes and ears are in better alignment. But really, motion sickness in this regard is very much a control issue, because you find out that if it's better in the passenger seat, if you slide over to the driver's seat, it might be completely gone. And your vision range didn't change there. The only thing that changed was you're completely in control now. So being in the front seat gives you a greater sense of control. Being in the driver's seat gives you a complete sense of control. And so I would argue that a lot of car sickness is more of a control issue than anything else. But it does involve, obviously, these rotational and gravitational sensors. If you experience seasickness, let's say you're on a cruise ship, and even though it's a really big ship, that ship does rock back and forth a couple feet from one side to the other as it's in the waves. So if you're in your room, for example, your ears might be saying you're moving back and forth, and your eyes, because they're moving back and forth with the room, would say, no, there is no movement. And that fighting back and forth can very easily cause seasickness. The solution there, and be careful with this one, if you're so unbalanced that you can't stand up and walk reasonably straight, don't try this. But if you go up on deck, then your eyes can actually see to some degree the movement that is going on, and as soon as the eyes and ears agree with each other, problem solved. The symptoms, the sensation of being nauseous and everything else goes away because the source of that is satisfied. The eyes see the movement, the ears detect the movement, and everybody agrees. Hopefully this was informative and you learned a lot and everything made sense. Thanks for joining us. We'll see you next time.